The aircraft was conceived in an era of absolute confidence. On drafting tables and high-performance computing clusters, the airframe of the F-22 Raptor was modeled as a seamless union of stealth geometry, composite materials, and titanium strength. Its skin was not merely a shell. It was a multi-layered system of radar-absorbing materials, advanced epoxy composites, and precision machine metallic substructures designed to endure extreme aerodynamic loads while remaining invisible to enemy sensors. Every panel, every fastener, every micron of thickness was optimized through iterative simulation. The aircraft was marketed not as resilient, but as dominant, immune to the constraints that had humbled previous generations of fighter aircraft. Engineers spoke in absolutes: absolute air superiority, absolute survivability, absolute control. In this architecture of confidence, the cockpit became a sealed ecosystem. Inside it, the pilot was promised not only protection from hostile fire, but protection from the atmosphere itself. At operational altitudes where the partial pressure of oxygen falls below levels compatible with human consciousness, the F-22's life support architecture was designed to function as flawlessly as its stealth profile. The environmental control system drew superheated, high-pressure bleed air from the engines and routed it through a complex network of heat exchangers, pressure regulators, and filtration stages. At the center of this system was a technological statement: the onboard oxygen generation system. Unlike legacy fighters that relied on stored liquid oxygen, a system heavy, logistically complex, and vulnerable to leakage, the F-22 would manufacture breathable oxygen in real time. Molecular sieve beds, composed of engineered ceramic materials with precisely sized micropores, selectively adsorbed nitrogen while allowing oxygen to pass through. The result was oxygen-enriched air delivered directly to the pilot's mask, regulated dynamically according to altitude, workload, and cabin pressure. On paper, the system was elegant. It reduced weight, increased endurance, and eliminated a known hazard. In practice, it introduced a new category of risk: dependence on perfect material behavior at the microscopic scale. The design assumed that ceramic sieve materials would retain structural integrity under repeated thermal cycling, that seals would maintain elasticity over thousands of pressurization cycles, and that airflow would remain laminar through geometries calculated in controlled environments. What the design philosophy underestimated was the cumulative effect of operational reality: vibration, contamination, and thermal gradients acting simultaneously over time. The hidden flaw did not manifest as a single defective component. It emerged at the interfaces where dissimilar materials were forced to coexist under extreme conditions. The ceramic sieve beds expanded and contracted at rates different from their metallic housings. Polymer seals aged under heat and pressure, slowly hardening and shedding microscopic debris. Each flight introduced temperature swings of hundreds of degrees Celsius between ground operations and high-altitude cruise. These swings imposed cyclic stresses that concentrated at boundaries invisible to routine inspection. Stress concentration factors rose locally, far exceeding the averaged values predicted by finite element analysis. The materials were behaving exactly as physics dictated, just not as the designers had assumed. Within the ceramic sieve beds, microfractures began to form. These fractures were not catastrophic cracks, but hairline discontinuities measured in microns. Their presence subtly altered internal flow paths. Nitrogen adsorption efficiency declined incrementally, not enough to trigger alarms or fail acceptance tests, but enough to destabilize oxygen concentration under peak demand. Fluid dynamics inside the system shifted from predictable laminar flow toward localized turbulence. Pressure differentials oscillated. The system's output began to fluctuate within margins deemed acceptable by specification, yet perilously close to physiological thresholds. This invisible degradation unfolded silently over hundreds of sorties. Each pressurization cycle advanced crack propagation according to the unforgiving mathematics of fracture mechanics. Paris law describes how crack growth accelerates once a critical stress intensity factor is reached, but in this case the growth was slow, insidious, and distributed. No single flight caused failure. Instead, each flight nudged the system closer to a state where performance margins vanished. The drama was occurring inside the material itself, beyond the reach of sensors calibrated for macroscopic failure. The first warning signs were human. Pilots reported symptoms inconsistent with mechanical malfunction, lightheadedness, confusion, delayed reaction times, tingling sensations, headaches. These were classic indicators of hypoxia, yet the aircraft's systems reported normal operation. Oxygen concentration readings remained within specification. Cabin pressure was nominal. The machine insisted it was healthy. The pilot's body disagreed. In high-G maneuvers, where blood is pulled away from the brain and oxygen demand spikes, the compromised system failed to respond with sufficient consistency. Even brief drops in oxygen partial pressure impaired cognitive function. Decision-making slowed. Situational awareness degraded. In an aircraft traveling at supersonic speeds, milliseconds matter. The catastrophic sequence was therefore not mechanical violence, but physiological collapse. At altitude, under sustained workload, the pilot became the weakest component in a system optimized beyond human tolerance. Episodes escalated. In several cases, pilots experienced near loss of consciousness while flying one of the most complex machines ever built. The physics were merciless. Hypoxia does not announce itself with pain or alarms. It steals capability quietly, narrowing vision, dulling judgment, erasing time. Training could not compensate for biology. The immediate aftermath was confusion bordering on denial. There was no smoking crater, no twisted wreckage demanding answers. Instead, there were medical reports, grounding orders, partial returns to flight, and renewed restrictions. Confidence fractured. The fleet was grounded not because it had failed structurally, but because it could no longer be trusted to sustain life reliably. Engineers faced a crisis of epistemology. The data said one thing, the pilot's experiences said another. In response, the investigation turned forensic. Components were removed and dissected in laboratory environments. Molecular sieve beds were examined under scanning electron microscopes. Microfractures, invisible during routine inspection, became unmistakable at high magnification. Chemical analyses revealed trace contaminants embedded within ceramic pores, byproducts of seal degradation and lubricants carried by bleed air. Thermal imaging studies showed uneven temperature distributions during operation, confirming the presence of unmodeled gradients. The system had not failed randomly. It had failed precisely according to physical laws that had been underestimated. The root cause was not a single material defect or manufacturing error. It was systemic hubris. The belief that advanced materials, once validated in controlled testing, would behave identically under decades of operational stress. The assumption that performance margins were immutable. The failure lay not in ignorance, but in overconfidence. Confidence that complexity equaled robustness, that redundancy compensated for fragility at the microscopic scale. The engineering legacy was immediate and far-reaching. Design revisions introduced additional sensors capable of detecting subtle oxygen fluctuations. Thermal management strategies were reevaluated. Certification protocols expanded to include long-term microstructural aging and contamination pathways. The event reshaped how life support systems were evaluated, shifting focus from nominal performance to degradation over time. The F-22's oxygen crisis became a cautionary case study taught not only to pilots, but to engineers. In the end, the aircraft did not fall from the sky. It was something far more unsettling. It revealed that even the most advanced machines are constrained by the smallest flaws. That supremacy at the macro scale can be undone by failure at the micro scale. That engineering brilliance, when paired with arrogance, produces systems that appear invincible, until they quietly are not. The history of aviation is written with steel, ingenuity, and the will to challenge limits. Welcome to the Vault. Confidence did not collapse all at once. It eroded under scrutiny. Once the initial forensic indicators pointed toward oxygen system instability, the investigation expanded outward, moving beyond individual components and into the architecture of the aircraft itself. The F-22 had been designed as an integrated organism. Its stealth skin, internal volume constraints, and thermal signature requirements forced systems into tight physical proximity. Ducting for the environmental control system ran through confined spaces bordered by composite skins and titanium frames. Heat generated by avionics and engines bled into these volumes, creating localized thermal environments far more complex than those assumed during certification. The oxygen system was not isolated. It was embedded within a thermal and structural ecosystem that evolved over time. Material science now became the central character. The ceramic molecular sieve beds, selected for their adsorption efficiency and durability, were never intended to operate in isolation from the rest of the aircraft's structural behavior. Each sortie exposed them to vibration spectra generated by supercruise, high angle of attack maneuvers, and rapid throttle changes. These vibrations transmitted through metallic housings into brittle ceramic matrices. Even subcritical vibration amplitudes, when applied repeatedly, induced microdamage. Grain boundaries within the ceramic experienced shear stresses that accumulated incrementally. Over hundreds of hours, this damage altered pore geometry. Nitrogen adsorption efficiency declined not linearly, but unpredictably. Thermal expansion mismatches compounded the problem. Titanium, aluminum alloys, ceramics, and polymer seals each expanded and contracted at different rates. During climb, rapid temperature drops induced tensile stresses in components designed primarily for compression. During descent, reheating reversed these stresses. This cyclic loading acted like a microscopic hammer, striking the same interfaces repeatedly. Fatigue does not require large forces, it requires repetition. The designers had accounted for fatigue in wings and fuselage skins. They had not fully accounted for fatigue in life support materials hidden deep within the airframe. As degradation progressed, system behavior became nonlinear. Oxygen concentration outputs remained within allowable limits during steady-state conditions, but transient events exposed vulnerability. High G turns increased pilot oxygen demand precisely when pressure fluctuations inside the system were most pronounced. Flow instabilities amplified small material imperfections into measurable physiological consequences. The system did not fail outright, it oscillated. These oscillations were enough to disrupt human cognition without triggering system-level warnings. The investigation also revealed an uncomfortable truth about testing philosophy. Certification had focused on proving that the system met specifications under defined conditions. What it did not adequately explore was how those specifications drifted as materials aged. Long-duration endurance testing, while extensive, could not fully replicate the combined effects of operational vibration, contamination, and thermal cycling experienced in frontline service. The aircraft had passed its tests. Reality had changed the parameters. As evidence mounted, the narrative shifted from isolated malfunction to systemic vulnerability. Engineers reconstructed operational histories, correlating pilot reports with flight profiles and environmental data. Patterns emerged. Certain altitudes, maneuver profiles, and mission durations correlated with higher incidence of symptoms. The aircraft was not betraying its pilots randomly. It was responding consistently to conditions that pushed a marginal system beyond its comfort zone. Mitigation efforts followed. Interim solutions included revised breathing protocols, backup oxygen sources, and operational restrictions. Yet these measures addressed symptoms, not cause. Deeper redesigns were required. Materials were reevaluated. Alternative sieve compositions were tested. Seal materials were reformulated to reduce particulate shedding. Duct geometries were modified to smooth airflow and minimize turbulence. Thermal insulation strategies were revised to reduce gradients. Each change acknowledged a fundamental lesson. Complexity demands humility. The cultural impact within the engineering community was profound. The F-22 had been a symbol of technological supremacy. Its oxygen crisis punctured that narrative. It reminded designers that innovation does not exempt a system from the laws of physics, that stealth and speed do not protect against fatigue and entropy. The aircraft remained formidable, but its mythology was tempered by reality. In time, confidence returned, not the blind confidence of the drawing board, but a harder, earned confidence rooted in understanding. The F-22 continued to fly. Its systems improved, its limitations acknowledged. The episode entered the annals of aviation not as a failure of ambition, but as a failure of assumption. It underscored a truth as old as flight itself. The most dangerous flaws are not the ones that shatter metal, but the ones that quietly erode margins until nothing remains between success and catastrophe. The story did not end with a crash. It ended with restraint, with redesigned protocols, with an industry reminded that every molecule matters, that every interface is a potential fault line, and that the human at the center of the machine is both its purpose and its ultimate constraint. As corrective measures were implemented and flight operations cautiously resumed, investigators continued to dig deeper, driven by a growing realization that the oxygen issue was not an isolated subsystem anomaly, but a manifestation of deeper systemic interactions. Attention shifted to the broader environmental control system architecture and its intimate relationship with the aircraft's stealth-driven design compromises. The F-22's internal volume was brutally constrained by radar cross-section requirements. Sharp angles, serpentine ducts, and compact bays minimized radar reflections, but also forced airflow paths into complex geometries. These geometries increased pressure losses, amplified turbulence, and created zones where temperature and humidity fluctuated far more aggressively than anticipated during design reviews. Within these confined passages, bleed air carried not only heat and pressure, but microscopic contaminants. Trace amounts of engine oil vapor, hydraulic mist, and degraded polymer particles migrated through the system. Individually insignificant, collectively they accumulated. Over time, these contaminants coated internal surfaces, including the molecular sieve beds. Adsorption efficiency declined further, not because the ceramic material had failed completely, but because its active surfaces were slowly being masked. This phenomenon was well understood in industrial gas separation systems, yet it had been underestimated in an airborne environment where maintenance intervals were dictated by operational tempo rather than laboratory ideal conditions. The degradation curve steepened. What began as marginal inefficiency evolved into measurable instability. Pressure sensors recorded oscillations that were initially dismissed as noise. Software filters smoothed the data, preserving clean readouts for pilots and maintenance crews. In doing so, they obscured early warning signs. The system was behaving within its programmed expectations, but those expectations were based on assumptions that no longer held true. The aircraft was flying with a model of itself that was slowly diverging from reality. Physiologically, the effects became more pronounced. Pilots experienced subtle but repeatable cognitive impairments during specific mission phases. High-altitude cruise combined with prolonged maneuvering produced conditions where oxygen delivery lagged demand. The brain, exquisitely sensitive to oxygen deprivation, responded predictably. Reaction times increased. Fine motor control degraded. Memory gaps appeared. These were not dramatic blackouts. They were degradations of edge performance, the very margin that defined fifth-generation air combat. In an aircraft designed to dominate beyond visual range, losing cognitive sharpness for even seconds was unacceptable. The investigation broadened again, now incorporating aerospace medicine. Blood oxygen saturation data, pilot biometrics, and flight profiles were correlated with system telemetry. The results were damning. There were moments where oxygen partial pressure dipped just low enough to impair higher-order cognitive functions without triggering overt hypoxic alarms. The system had been designed to prevent loss of consciousness, not to preserve peak cognitive performance. This distinction, subtle on paper, was decisive in combat reality. The aircraft was technically safe, yet operationally compromised. Engineering teams faced an uncomfortable reckoning. The problem was not that the system failed to meet its minimum requirements. It was that those requirements had been insufficiently defined. Human performance had been treated as a threshold phenomenon, awake or unconscious, rather than a gradient. The F-22 had been optimized for structural and electronic superiority, but the human-machine interface had been engineered to the lowest acceptable physiological baseline. In pushing the aircraft to the edge of physics, the designers had brought the pilot with it, without fully accounting for the cost. Redesigned efforts accelerated. Software was updated to expose previously filtered data, allowing maintainers to see raw pressure and concentration fluctuations. Additional sensors were installed to monitor humidity, temperature, and contaminant levels within the oxygen system. These sensors revealed a dynamic environment far more chaotic than expected. Oxygen purity varied not only with altitude, but with engine throttle settings, mission duration, and even ambient weather conditions on the ground before takeoff. The system was sensitive to initial conditions in a way that had not been modeled. material solutions followed. New ceramic formulations were tested with improved resistance to microfracture and contamination. Seal materials were replaced with compounds exhibiting lower outgassing and particulate generation. Duct coatings were revised to reduce adhesion of contaminants. Thermal isolation was improved to smooth gradients and reduce cyclic stress. Each fix addressed a specific failure mode, yet collectively they acknowledged a larger truth. The original design had been too tightly optimized, leaving no slack for entropy. As these changes were implemented, the narrative surrounding the F-22 evolved. Publicly, the aircraft remained a symbol of unmatched capability. Internally, it became a lesson in the limits of predictive engineering. Engineers revisited early design decisions with new eyes. Trade studies once resolved in favor of weight savings or stealth performance were reevaluated in light of life cycle resilience. The oxygen crisis forced a rebalancing of priorities. Absolute performance gave way to sustainable performance. The implications extended beyond a single aircraft. Lessons learned were fed forward into newer platforms. Designers of next-generation fighters incorporated more generous system margins, more transparent sensor data, and more conservative assumptions about material aging. Human performance metrics were elevated in importance, treated not as constraints, but as design drivers. The F-22's experience reshaped certification philosophy, emphasizing degradation pathways and long-term stability over initial compliance. In retrospect, the crisis was inevitable. The aircraft represented a convergence of extreme requirements: stealth, speed, agility, and endurance. Each requirement pushed systems toward their limits. Where those limits intersected, vulnerability emerged. The oxygen system became the focal point not because it was uniquely flawed, but because it sat at the intersection of materials science, thermodynamics, fluid dynamics, and human physiology. It was the place where abstract equations met living tissue. By the time the fleet returned to sustained operations, confidence had been rebuilt on firmer ground. Not the confidence of invincibility, but of understanding. Pilots trusted the aircraft again, not because it was perfect, but because its imperfections were known and managed. Engineers trusted their models again, not because they were complete, but because they were continually validated against reality. The F-22 did not lose its place in history as a technological marvel. Instead, it gained an additional chapter, one written not in speed or stealth, but in humility. A reminder that in aviation, the smallest deviations can have outsized consequences. That systems designed to support life deserve the same scrutiny as those designed to deliver weapons. And that progress is not measured solely by how far boundaries are pushed, but by how responsibly they are respected. As operations stabilized and redesigned components entered service, the investigation reached its most uncomfortable phase. Attention turned away from fixes and toward accountability, not in a legal sense, but in an intellectual one. Engineers reconstructed the original design assumptions that had governed the F-22's life support architecture. They examined early trade studies, requirement documents, and certification thresholds. What emerged was a pattern familiar to aerospace history, a chain of rational decisions that, when combined, produced an irrational outcome. The oxygen system had never been designed to fail catastrophically. It was designed to fail gracefully. Margins were calculated around preventing pilot incapacitation, not preserving peak neurocognitive performance under extreme operational stress. This distinction was subtle, buried in requirement language and certification logic. Hypoxia protection was framed as a binary problem, consciousness versus unconsciousness. But biology does not operate in binaries. Cognitive degradation begins well before loss of consciousness, and in high-performance aviation, that degradation is operationally lethal long before it becomes medically dramatic. The F-22's designers had relied heavily on probabilistic risk assessments. These assessments modeled failure likelihoods of components based on material properties, cycle counts, and historical analogs. Yet the oxygen system was unprecedented in its integration and operational envelope. There were no true analogs. The probabilistic models were therefore built on optimistic assumptions, extrapolated from industrial oxygen separation systems and earlier generation aircraft operating at lower performance thresholds. The models were mathematically sound, Their inputs were incomplete. As forensic work continued, investigators identified another critical factor: system coupling. The oxygen system did not exist in isolation. It was dynamically coupled to engine behavior, avionics heat loads, and pilot workload. Changes in throttle altered bleed air characteristics. Avionics cooling demands altered thermal flows. Pilot breathing patterns under stress altered demand profiles. Each coupling introduced feedback loops. Some were stabilizing, others were destabilizing. In complex systems, destabilizing feedback does not announce itself loudly. It manifests as oscillation, drift, and sensitivity to initial conditions. Flight data revealed that certain mission profiles consistently pushed the system into these unstable regimes. Extended high-altitude loiter followed by aggressive maneuvering produced the most severe fluctuations in oxygen delivery. The system's control logic, designed to smooth transitions, lagged behind rapid changes in demand. That lag, measured in seconds, was sufficient to induce transient hypoxia. From an engineering standpoint, the system was behaving as designed. From a human standpoint, it was failing its purpose. The most damning realization was this: no single fix could fully eliminate the problem. The oxygen crisis was not the result of one bad component or one flawed algorithm. It was the emergent property of an ultra-optimized machine operating at the edge of multiple physical domains simultaneously. Every optimization had reduced redundancy. Every weight saving had narrowed margins. Every stealth-driven constraint had compressed system volumes and increased thermal density. The aircraft had become exquisitely capable and exquisitely sensitive. This realization forced a philosophical shift. Engineers began to speak openly about fragility. Not weakness, but fragility. The tendency of a system to lose functionality rapidly once pushed beyond a narrow operating envelope. The F-22 was not fragile in combat survivability. It was fragile in sustainment of human performance. The pilot, once assumed to be buffered by technology, was now recognized as directly exposed to the consequences of micro-level material behavior. Long-term mitigation strategies reflected this shift. Operational doctrine was revised. Mission planning incorporated oxygen system considerations alongside fuel and weapons. Pilots were trained to recognize early cognitive symptoms and abort missions without stigma. Backup oxygen provisions were enhanced, even at the cost of weight and volume. These were not elegant solutions. They were pragmatic acknowledgments of reality. From a materials science perspective, the investigation yielded uncomfortable lessons. Advanced ceramics, while exceptionally capable, are unforgiving of design oversights. Their strength lies in controlled environments. In dynamically coupled systems with vibration, contamination, and thermal cycling, their failure modes become complex and difficult to predict. The F-22 experience reinforced the importance of life cycle testing that goes beyond accelerated fatigue and into realistic operational simulation. Materials do not merely age, they evolve under stress. The broader aerospace community took notice. Internal briefings circulated across manufacturers and defense agencies. Quietly, design philosophies began to shift. Engineers became more skeptical of perfect solutions. Redundancy regained respect. Simplicity, once seen as a limitation, was reevaluated as a form of robustness. Human factors engineers gained greater influence in early design phases. The oxygen crisis had demonstrated that supporting the pilot was not a secondary concern. It was a primary system requirement. In the years that followed, the F-22 story was often misunderstood in public discourse. It was framed as a flaw in an otherwise flawless aircraft. Internally, it was understood as something more instructive, a boundary case. The Raptor had gone further into the performance envelope than any fighter before it. In doing so, it revealed where the envelope began to tear, not in metal, but in assumptions. The aircraft continued to fly. Its combat capability remained unmatched. Yet it carried with it a permanent lesson etched into design manuals and institutional memory. The lesson was not that engineers had failed, but that success had blinded them to risk. When systems become too complex to fully intuit, humility must replace certainty. When margins shrink to optimize performance, vigilance must replace confidence. In the end, The oxygen crisis did not diminish the F-22's legacy. It deepened it. The aircraft became a symbol not only of what engineering can achieve, but of what it must respect. Physics does not negotiate. Materials do not forgive. Biology does not adapt on command. Every aircraft is a compromise between ambition and reality. The F-22 Raptor stands as a reminder that the most dangerous failures are not explosive. They are quiet. They live in microns, milliseconds, and assumptions left unquestioned. They do not destroy machines outright. They erode trust, margin by margin, until the system is forced to confront its limits. And that confrontation between human ambition and physical law is where the true story of aviation is written. The final reckoning arrived not with a dramatic incident, but with institutional acceptance. After years of investigation, redesign, operational mitigation, and cultural adjustment, the F-22's oxygen crisis reached its last and most consequential phase, codification. What had once been treated as an anomaly was now formally embedded into doctrine, engineering guidance, and design philosophy. The problem was no longer something to be fixed. It was something to be understood, remembered, and never repeated. In official assessments, language became more precise and more cautious. The aircraft was no longer described as operating with adequate physiological support under all conditions. Instead, documentation acknowledged operational sensitivities and environmental dependencies. These were not euphemisms. They were admissions that the system's behavior was inseparable from context. Oxygen delivery could not be evaluated in isolation from mission profile, maintenance history, material aging, or pilot workload. The aircraft had forced the institution to abandon reductionism in favor of systems thinking. From an engineering standpoint, this marked a turning point. The oxygen system had exposed the limits of deterministic design and highly coupled environments. Traditional aerospace engineering relies on breaking complex machines into subsystems, validating each independently, and then integrating them with confidence that compliance at the component level ensures safety at the system level. The F-22 demonstrated the flaw in that logic. Subsystems can be individually compliant and collectively vulnerable. Integration is not additive, it is transformative. The most profound lesson lay in how microscopic phenomena scaled into macroscopic consequence. Microfractures in ceramic sieve beds altered adsorption efficiency by fractions of a percent. Thermal gradients shifted seal behavior by microns. Contaminants accumulated at rates measured in micrograms per hour. None of these values appeared threatening on their own. Yet together, over time, they reshaped the system's behavior. This was materials science operating in its most unforgiving regime, long-term, coupled degradation under variable load. As a result, certification philosophy evolved. New standards emphasized not just initial performance, but performance decay. Engineers were required to model how systems aged, not ideally, but realistically. Maintenance schedules were rewritten to account for degradation pathways previously ignored. Sensors were no longer optimized solely for alarm thresholds, but for trend detection. Subtle drift became as important as sudden failure. In life support systems especially, the margin between acceptable and dangerous was redefined. The human element, once treated as an endpoint, moved to the center of design. Aerospace medicine gained a stronger voice in engineering reviews. Cognitive performance metrics were integrated into system requirements. Designers were forced to confront a difficult truth. Protecting consciousness is not the same as preserving capability. An aircraft that keeps its pilot alive but cognitively compromised has failed its mission before a weapon is ever fired. Operational culture changed accordingly. Pilots were no longer expected to endure unexplained symptoms in silence. Reporting protocols were strengthened. Abort decisions were normalized. The stigma once associated with calling it early diminished. The institution learned that silence was the most dangerous failure mode of all. Machines fail detectably. Humans often do not. With time, the narrative surrounding the F-22 matured. It was no longer framed as a cautionary tale of a flawed aircraft, but as an inflection point in aerospace engineering. The Raptor had reached a level of integration and performance where traditional safety margins collapsed. It revealed that at the edge of capability, systems behave less like machines and more like ecosystems, sensitive, interdependent, and prone to emergent behavior. This realization rippled outward. Future platforms absorbed the lesson quietly. Designs incorporated greater physiological margin, even at the expense of raw performance. Redundancy returned where it had been optimized away. Engineers resisted the temptation to chase perfection in simulation without equal respect for entropy in service. The industry became more skeptical of claims that any system was solved. The irony was inescapable. The F-22 had been designed to dominate environments hostile to human life. In doing so, it had exposed how fragile human-machine integration truly was. The aircraft could outrun missiles, evade radar, and defeat adversaries, but it could not escape the fundamental constraints of biology and materials science. No amount of computational power could repeal those laws. In the end, the aircraft endured. It continued to serve as a cornerstone of air superiority. Its pilots flew with renewed trust, not blind trust, but informed trust. Engineers supported it with deeper understanding, not just better tools. The system, once shaken by uncertainty, stabilized through knowledge rather than denial. The legacy of the oxygen crisis was not written in accident reports or wreckage analysis. It was written in revised requirements, quieter confidence, and a recalibrated relationship between ambition and restraint. It reminded an entire field that progress is not linear, that pushing boundaries inevitably reveals new failure modes, and that the true measure of engineering excellence is not how rarely systems fail, but how honestly those failures are confronted. Aviation history is often told through dramatic moments, first flights, record speeds, fiery crashes. Yet its most important chapters are sometimes invisible, unfolding inside materials, algorithms, and assumptions. The F-22 story belongs to that quieter history, a history where the enemy was not an opposing aircraft, but the unintended consequences of success itself. Because in aviation, the greatest risk is never ignorance alone. It is certainty without humility. And every generation of engineers must relearn that lesson, one system at a time. The history of aviation is written with steel, ingenuity, and the will to challenge limits. Welcome to the Vault.